Greetings. So what is an earthquake? When you think of an earthquake, what is it that crosses your mind? What is it that you think an earthquake is? How often do they happen? How bad are they? Is it a good thing or are they bad things? Most people think of earthquakes, think of something like this. Panic, destruction, mayhem, injuries, deaths. That's what most people think of when they think of an earthquake. So let's think about what an earthquake actually is. In layman's terms, it essentially is two pieces of the earth, or tectonic plates to be technical, suddenly slipping past one another. A sudden displacement or a fracture along the outermost layers of the earth. And we record this. We know this happens not just because of earthquakes, but we record this and measure these earthquakes using tools called seismographs. They measure the size or the fracture, the amount of actual slip that's actually occurring on the outermost layer of that, or the crust of the earth. So the question is, in July and August 2016, for earthquakes, what happened? That's the core question we wanted to set out to understand. And when we first looked at this data, you can very quickly discern patterns. You can see groupings that are occurring. You can see groups here in Alaska where there's a preponderance of earthquakes occurring, tons on the west coast. Not so much here in the middle of the ocean, although there is some in Hawaii. We see a bunch of them over here in the Solomon Islands area. We see them over here along the Japan. Think Fukushima nuclear power plant, the earthquakes that happen there that damage the nuclear power plant. Not too many recorded in Africa, which is surprising. And again, the ocean seems to be fairly bare of recorded earthquakes. So this data is sourced from the U.S. Geological Service, by the way. And again, we're looking at data that occurred for roughly 1 month of time between July and August 2016. Now, when we look at this, again, we're seeing groupings, we're seeing sizes. Many of these earthquakes are happening are much larger. So if we focus over here on some of these, there's a size 4.3. We have sizes of average of 4.9. But when we come over and look at Alaska, which has tons of earthquakes, the size and the averages are much smaller. We're looking at sizes of 1. And so we can see right off the bat that there's something in the data that's not quite normal. Things are a little bit off here. So we went to do an analysis of what were those differences. When we look at this, remember that this is the U.S. Geological Service. We see a huge frequency number of events occurring. This isn't the size of the earthquake or the importance of it or other measures, simply how frequently are they even being counted. And we see that Alaska and California are by far the most. Alaska and California together comprise over 68% of all the data that's been collected by the U.S. Geological Service. That's more than 2/3 of the world's earthquakes that are recorded. So clearly there's something happening here. So we decided to look, focus based on the fact that this is the U.S. Geological Service. We wanted to focus on what were the top 5 things, what were the top highest frequencies. So when we do that, we see California, Alaska, Nevada, Hawaii, and Washington. So doing a deep dive into those top 5 earthquake locations, we see frequency, magnitude, and significance measures. So we have a trend analysis here using line graphs for magnitude here and significance to the right. And we can see visually, there's actually quite a bit of similarities The patterns are not exact, they're not the same, but we see very similar activities, a high correlation occurring between these systems. Again, Alaska and California, there's preponderance of the data, but we also have Hawaii, Nevada, and Washington. Together, all 5 of these represent 88.2% of all the data that was documented by the U.S. Geological Service during the time spans between July and August that was provided in the original data set provided by the University of Virginia Technology. So the next question becomes, what are the things about this data that we want to look at? What we have here essentially is an outstanding opportunity to look at not only an analysis, but a potential prototype for an analytic tool to be used as an operational tool. So this is something that can help scientists as well as people in various industries, and we'll talk about that a little bit more in a moment. So let me demonstrate what that looks like. So we can press this play button over here, and we can see daily trends occurring. So every day there's a different earthquake, there's different activities, but the frequency of these earthquakes is constant. However, the size of those earthquakes is minimal. So I'm gonna hit pause and just take a random data set, hover my mouse over this, and say magnitude of 1. If we come over to California, take another random data set, magnitude of 0.5, less than 1. Take another random one here in Washington, 0.17. So what we're seeing is previously in the global area, we saw magnitudes of 4 and 5. When we come and focus on the top 5 locations that have higher volumes or counts that are occurring, these earthquakes are smaller in magnitude. They're smaller in significance, but they're being counted more often by seismographic systems. This leads us to believe that the U.S. Geological Service has stations set up in specific areas that are far more sensitive and far more accurate, as well as simply just placed, right? They may not be located in other locations, but the locations that are here are picking up all of the earthquakes, both big and small. What we notice is that the frequency is actually quite high. So there's a lot of frequency, but the magnitude is low, the significance is low. However, we also note that there are constant locations. So again, if you think about the global view we saw a moment ago, and we look at this daily view, and we'll hit play again to watch this play out, you can see that this is changing on a regular basis. So now we come to the concept of the prototype. So I'm gonna hit pause again to talk about the prototype. So if you were a financial underwriter, or an analyst, or a construction investor, or even a government reporting agency or watch officer that was responsible for public safety, you could use a tool like this. So taking the data set and then using Watson IBM Analytics, you could conceptually create a dashboard that would look very similar to this. Think of this as a prototype. And you could focus on multiple different areas for your analysis. You could simply click over here in the frequency analyzer to say what's happening in California. And you'll have a change over here that'll show you all the things that are happening in California, where all the earthquake locations have been, how often are they. So for example, they're very frequent over here in San Francisco, but here in the middle of the state, there's hardly anything. If you look over here on the borderline between Nevada and California, there's a lot. So if we click on Nevada, we can see, again, there is a constant pattern that is occurring between those earthquakes. And you can see that patterns up here in the trend analysis, right? So you can see the frequency that's occurring is higher. So this is the sum of the magnitude. So all of these earthquakes on a daily basis, so day 1, day 2, day 3, day 4, day 5 of the month. How often are those earthquakes occurring? What is the magnitude and what is the significance? And again, it's fairly low. So if you were a real estate investor, or an insurance underwriter, there's far less likely activity is going to happen in Nevada than, say, California or Alaska. So right off the bat, we're able to see investment opportunities, we're able to see insurance, we're able to assign risk. If you're a watch officer, you can understand where to focus your incident response. So if you're a female coordination manager, you know where the most likely occurrences are simply by preponderance and probability statements of location frequencies. There's tons of different ways to take this type of data across multiple different industries, across multiple different responsibilities, both financial and safety-based data, and be able to operationalize this data along with the analytic tool set in this visual graph. And at this point, you don't need to be a data scientist either. Once this is set up, you need someone who understands data to create it initially. But once this is stood up, this is something that can be working and operating in this, in a security operations center or a watch center on a regular basis, or an insurance underwriter can simply come in here and say, where are the locations? If I'm going to have a property location of, you know, Las Vegas, right? How often are earthquakes going to have? So you could take this, or you could even drive down deeper. If we enrich this data to have zip codes, we could drive down zip code information as well. We have the longitude and latitude, we simply haven't included the zip codes. So there's additional ways that you could add or enrich this, but the concept there, the prototype of this dashboard, is exceptionally useful. So in conclusion, we've taken the U.S. Geological Service data, and we've identified some fidelity issues with that data. And those fidelity issues are understandable, but based off that fidelity issues, we decided to focus down on 5 specific areas that had far more fidelity and far more data set information. We then did a detailed analysis, and we proposed how this data could be used. And once we get to a point where the data is enriched in other locations, so if it's data like as much detail as we're seeing here with Nevada and California, Washington, and Hawaii, if we're able to take this data and get other locations such as Japan, for example, or anywhere in the world, quite frankly, you'll be able to operationalize this data significantly for multiple industries, for multiple different settings, for public safety, for making money, understanding where to do your construction, understanding if you're doing construction that you need to be earthquake protected, and so forth. So I want to say thank you for your time. I hope you found this useful. If you have any questions, please feel free to reach out to us. My name is Jeffrey Watson, and my partner is Gene Hill. Have a great day.